I'm going to share it right here. And here we go. Can you hear me? First check is, can you hear me? Can you see me? Can you hear me? And how's it going? That's number one. Let me do a little computer work here so I can see. Were you able to find me? And can you hear me? And can you see me? Yay! We're in great shape then. Yes! Okay, sorry that took so long. In the future, I'll just start here and not have to switch between my headphones and switch my webcam over or anything. And so we won't have to have that break in between, at least not as long. Okay, so now what we're going to do is learn about parent functions, which is what we should have done, a week and a half ago. So we'll start with that, and we're gonna learn parent functions, and then I'm going to tell you what you're doing for that first homework task. So your first homework task is just going to be to graph all 7 functions, and I'm going to tell you exactly what I want you to graph on those 7 functions. Like, I'm going to tell you exactly which points to put on there and everything. So I'm basically doing your homework for you. So if you did it really neat as I went along, you can have that first task done. Now, it's really important that we learn these 7 parent functions and we learn the points that that I'm about to show you, because we're going to use those when we talk transformations, and then all throughout here for a while we're going to be looking at these parent functions over and over and over again, and it's just really important that you know the shapes and you know the points. Normally, when we're in class, your daily quiz next time would be to graph the 7 parent functions in 5 minutes. So that would be your task for the next time. So you want to learn it that well. You want to know these parent functions and know those 5 points that I'm going to show you that go on each one, and know the shape. And you want to know them that well so that you can just pop them out. Okay, so with all that information, let's just start with some parent functions. And what the parent function is just the simplest form of a specific family or a specific function. And remember, when we talked about functions, we did that before spring break, we talked about functions. But I'll remind you that a function is just, we have an input and then we have some output. And every input has one unique output, has exactly one output. And remember, we did that vertical line test. So, if I have something like, if I have a graph that looks like this, it passes the vertical line test. In other words, if I draw a vertical line anywhere on there, I only hit it one time. So that means this x value here just has one y value. Or that x value there has one y value. And I think in class I even talked about a function, in regards to like the Coke machine. When I hit that Dr. Pepper button, out comes a Dr. Pepper. The next time I hit the Dr. Pepper button, out comes a Dr. Pepper. Every time I hit that Dr. Pepper button, out better come a Dr. Pepper. If I get a Coke, it's not functioning. And it's the same idea here with a function, that every time I put in an input, I should get out the exact same output. So, if it's something like this, well then I can draw that vertical line I hit twice. This is not a function. That's not a function. So we're talking about functions, and then I'm going to teach you 7, we're going to talk about 7 different functions, and we're going to look at the simplest of those, the parents of those. So let's start with the first one. Our first one is our linear function, and we've actually already graphed linear functions. So remember, when I talk about linear functions, I know back when we did those, back before spring break, maybe you remember that y equals mx plus b form, that slope-intercept form of the linear function. where the m was the slope and the b was our y-intercept. Remember doing that? I don't know, that's been 2 weeks or longer. So some examples of some linear functions might look like this. Here's a family member where my slope is 3 and my y-intercept is at 0, -4. Or maybe here's another one in that fancy function notation. Remember, we can just replace the y with the f of x. That's our function notation. And so here's a family member, 1/2 x plus 3 or something. There's another linear function. Or we could even put it in a form like this. As long as my x and my y aren't touching, and that x is not in like an absolute value sign, the x is not under a square root, it's not got any little house around it, and then the degree of it is 1. So the degree of this thing is just a 1. So therefore, this is a linear, that's what makes it a linear function. Now the simplest of these is y equals x. That's the parent. You know, if I made my m1 and my b 0, so my slope here is 1, and my y-intercept is at 0, 0, this is that parent of my lines. So, or I could write it in function notation, y equals x. And all of these guys are going to look something like this. They're going to make a line. They're going to look one of those ways. And so we're going to graph the parent. And when I think about my x values, first I'm going to make my xy table just to graph some points on it. And when I think about those x values, is there a number that I put in for x that's going to cause me problems? Like that I can't put in for x. If I put in for x, I'm going to get out some non-real y value. Is there anything that I can put in for x that would cause a problem? Can you think of anything? Let's try something like 0. Let's see if I can put 0 in there. If I put in 0 for x, then if I put in 0 for x, I get out 0. So I have a point at 0, 0 on my graph. Okay, 0 worked just fine. Okay, what about a negative number? Let's try a negative number. If I put in a negative number for x, well then I get out a negative number for y. So a negative number works. In fact, there's a point at -1. When I put in -1, I get out -1. I could even put in some irrational number like the square root of 2. You know, if I made x the square root of 2, then my y is equal to square root of 2. I mean, that's not pretty to graph. I could graph it, but it's not a pretty thing to graph. So maybe we don't use that one. But it turns out I can put in any number that I want to for x. So we say that x value, when I'm talking about my x values, I'm talking about something called the domain. And next week, I'm going to have a whole lecture just on domain and range. But I'm going to show you this math talk and this math notation so that when we get to that domain and range talk next week, maybe it's not so complicated. So I can put in anything I want to for x. So we say that the domain of this, the domain is all real numbers. And I write it like this in set builder notation. Again, this is Math-Ease, and we're going to have a whole lecture on just domain, so it's okay if it's like confusing. That's all right. I'm just showing you now so we get lots of practice with it. This is x such that x is an element of the real numbers. In other words, x just can be anything. Another way to write that is in interval notation, where x can be anything from -infinity to +infinity. It can be any number. From -infinity all the way up to +infinity, x can be anything. That's all this says. Both of those say the same thing. And again, we're going to have a whole lecture on that. Don't freak out. Okay, so since I can use any numbers that I want to, I like to use these 5 numbers, -2, -1, 0, 1, and 2. And these are the 5 numbers I'm going to want you to use when we're talking about the linear functions. So I'm just going to put in -2 for x, and out comes, when I put in -2 for x, well then my y is also equal to -2. When I put in 1 for x, well then out comes 1 for y. When I put in 2 for x, well then out comes 2 for y. So I have these 5 points on this graph, -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. All right, we're going to graph that. So you guys got graph paper. Remember, I didn't make you buy a book. I didn't make you buy a calculator. You didn't buy anything except graph paper. So I'm hoping that you made those purchases before all the stores shut down. I'm hoping. If not, under the parent functions tab, I put graph paper. Maybe you can print it out so that you have some graph paper. I'm hoping. Okay, on graph paper. Find some graph paper. And on graph paper, I don't have graph paper on my board, darn it. Okay, so on graph paper, you're going to graph these 5 points. -2, -2. -2, -2. Remember, you walk and then you climb. -1, -1. Walk to the ladder and then climb down. 0, 0. 1, 1. 2, 2. Those are the 5 points that we just found on this graph. Now, x can be anything though. That's what that says. So there are spots in between here. Like for instance, if I put in 1/2 for x, I get out 1/2 for y. So over here at 1/2, 1/2, there's a point. And there's a point at 1/4, 1/4. And, 1.5 and 1.5. So these dots we're going to connect, and they go on. And in fact, I could put in 100 and I'd get out 100. We could go on forever and ever. So to show that, I'm going to put this line that goes on forever and ever. And remember, to show that it goes on forever and ever, we're going to put an arrow at the end. So the arrows are important too, to let me know that it keeps going. Next week when we talk about our domain, if it doesn't have that arrow, it means it stopped. So it's really important to put that arrow on there. And then we've got to connect it the other direction too, because at -1/2, -1/2, there's a spot. There's an infinite number of spots in between here. So we've got to connect those, and then again put those arrows on there. Then I want you to label your points on your graph. It's kind of like, your English teacher makes you start your sentences with a capital letter and put a period at the end. Well, in math, we like you to label your axis or label your points. You've got to label so that I know what our scale is on there. So I always just label my points 0, 0, 1, 1, 2, 2, -1, -1, and -2, -2. So just label those points for me. By the way, can you see the red? Is that working okay? So this is our linear function. I'll swap out, go back to black. I meant to graph in black and do the axis in red. So this is our linear. And our linear, this is the parent of the linear function. So you're just going to graph that, graph those 5 points nice and neatly, take a picture, upload it. That's the first of the 7 that you've got to turn in for parent functions. All right, let's do another one. Number 2 is quadratic. The second one we're going to do is our quadratic. Remember doing the quadratic formula? If you look in Math Lab chat, there's one of Mr. Leach singing the quadratic formula. There's a great little link in there for that to remind you about that quadratic formula. That's going to show up again in my class. I'm going to keep linking Mr. Leach singing it. Okay, so quadratic looks something like, I'll give you some family members first. Like maybe we've got something like this. Y equals 4x squared plus 3x plus 1. Or here's another family member. I've got, I don't know, 1/2 x squared minus 2. Sometimes they look in this form, and we'll see this next week too, where I've got x minus 3 squared plus a number out here. So what makes a quadratic a quadratic? The fact that the degree of that polynomial is 2. In other words, if I multiplied that out, the biggest degree or exponent I would have would be a 2. The biggest exponent I have here is a 2 on that x, and that's what makes it a quadratic. Now, all of these quadratics are going to take this shape. It's going to look like that parabola. They're going to look something like this. Or maybe they look like this. They're a smiley face or a frowny face. It's just what a quadratic looks like. Now, the most basic, or the parent of these guys, the simplest of them, is y equals x squared. So y equals x squared is our parent quadratic. We call it a quadratic function. Or using function notation, just replace the y with the f of x. And we've got f of x equals x squared. So those two things are the same thing. This is just our fancy math notation, or function notation. And let's ask again that same question. Is there a number that I cannot put in for x? In other words, is there a number I can put in that I put in for x that I don't get out a nice real number for y? That's really what I'm asking. So is there some number that I can't put in for x? Think about it for a minute. What about like 0? Can I put 0 in for x? Let's try it. If I put in 0 for x, well, 0 squared is 0. I like it, 0. Let's just try it and just see. Because there was that one function where putting in 0 was bad. Do you remember that? We'll get back to that. Okay, so that tells me that this y is equal to 0. So when I put in 0, out came 0. So that's a real number. That actually worked. It was a good try. Let's try another one. Can you think of another one that might not work? How about like, or doesn't give me a nice real number? How about like -1? I put in -1 for x. Take that and put it in for x. Well, what's -1 times -1? It's 1, right? So I've got a point there, so that is a real number also. So -1, 1 is another point on this graph. What about like a fraction? Can I put a fraction in here? I don't know. I know y'all don't want to put a fraction in there, but can I put a fraction in there? Let's try. So if I put in 1/2, that's 1/2 times 1/2. And remember, with fractions, we just multiply straight across, so we end up with 1/4. So sure enough, even a fraction works in there. We can even put in something like the square root of 2. You know, if I put in the square root of 2 in here, the square root of 2 would be squared, would be the square root of 2 times the square root of 2, which is the same thing as the square root of 4, which is just equal to 2. So I could put in even this ugly, 1.4-ish, that square root of 2. I don't want to put that in, but I could. I would get out a real number. So it turns out, once again, that my domain of this thing is all real numbers. The domain of a quadratic is also all real numbers. And this is just a fancy way. It's called, we're putting it in set notation. These things are help us build a set. And it says x such that x is an element of the real numbers. And again, we're going to have a whole lecture on that. Don't freak out too much. And our interval notation is from -infinity to +infinity. So that just says our x value can be anything. When my x value can be anything, I like to use these 5 values. -2, -1, 0, 1, and 2. And those are the 5 values I'm going to want you to, those are the 5 values I'm going to want you to graph with. And you're exactly right, Austin, that's exactly what happens. This squared and that square root kind of cancel each other out, because another way to think of it is this is 2 to the 1/2 squared. Well, 2 times that 1/2 gives me 2 to the first. So you're exactly right. They just cancel each other out. It's exactly it. You got it. Okay, so I'm going to put in these 5 numbers. So -2 squared, well, -2 times -2 is just a +4. And 1 times 1 is 1. And if I put 2 in for x, then 2 squared is 4. So these are 5 points on that quadratic parent. So we're going to graph those 5 points. And this time I'll do it better. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Y'all have nice graph paper, so it's going to look all nice and pretty. I'm going to graph these 5 points at -2, +4, -1, 1, 0, 0, 1, 1, and 2, 4. Graph those 5 points, and just like before, x can be anything, so that means there are points in between there. And in fact, we talked about there being a point at 1/2, 1/4, you know, so right about here there's a point. And so we just connect those dots, and it makes this U, this smiley face shape. So we have this nice shape like that. And there's our quadratic formula, our quadratic function. Our parent of that quadratic formula, function. Man, I want to say formula, but it's function. And again, I'm just going to label with my points, or you can label the axis to help out, but make sure that you've labeled so that your reader knows where those points are located. There you go. You've graphed your quadratic function. Yay! Okay, so there's number 2 done on your homework. You did the linear, and now you've drawn a quadratic function. Let's look at another parent function. How about this time we look at, let's see if you can guess what kind of function this is. I'll put a bunch of them up there and you see if you can guess what kind of function this is. And function notation here, here's a fancy one. What do you think? What kind of function is this? I put some crazy numbers. What if I did the square root of 2 times absolute value, 6x plus 4 absolute value minus 7? What kind of function do you think that is? Notice that all of them have certain symbols in there. You remember what those are called? Those symbols? Not for all of them, September, but for a lot of them. But not for all of them. Just the ones that their domain is all real numbers. So all of this one is called an absolute value function. Yay, way to go, Austin. Yes. Bonus points for Austin. Way to go. Absolute value function there. So the simplest of that guy is y equals the absolute value of x. Or in function notation there, absolute value of x. So this is our absolute value function. And this is the parent of those, that simplest one. So again, we have to think first. So to answer your question, September, we have to think first. If the domain is all real numbers, in other words, if I can use any number I want to for x, then yes, we're going to use -2, -1, 0, 1, and 2. But for some of our functions, we're going to have a restriction in there. It's not going to work so nicely. But for this one, let's look and see. Can I put in anything I want to for x again and get out a real number? In other words, if I make x 0, well, what is the absolute value of 0? Remember that absolute value is just the distance from 0. Or I can show you a fancy piecewise function that also defines it. So this y equals the absolute value of x. we define it this way, this function, if that is a positive number. In other words, if x is greater than or equal to x, then this is just equal to x. But if x is a negative number, that's what this says, if x is less than 0, then we define this as a negative x. So this is like the definition, the mathematical definition of an absolute value function here. This y equals the absolute value of x. We call that a piecewise function. So when it's positive, this is happening, and when it's negative, this is happening. And so when I put in 0, well, when it's 0, it's just equal to 0. Or 0 is 0 spots away from 0. So we can put in 0. Well, what about negative 1? Well, when I put in negative 1 for x, that's a negative value, so I do a negative of a negative, negative of negative 1, which makes that a positive 1. Or you just ask yourself, how far away is negative 1 from 0? It's one unit away. So there's a point here at negative 1, 1. So again, I can put in any number I want to for x and get out a real number. So my domain here is just like it was before. It is all real numbers, or anywhere from negative infinity to positive infinity. I can even put in something like 1/2, and I'm going to get out that same 1/2. That's a positive number, so I get out a half. Since I can put in any number I want to for x and get out a real number, I'm going to use those same 5 values, negative 2, negative 1, 0, 1, and 2. And then my output, well, when I put in negative 2, I end up with that's 2 spots away from 0. When I put in 1, I get out 1. When I put in 2, I get out 2. So again, you're going to graph those 5 points of this absolute value function. So, what did I do with that red? I'm going to graph those 5 points. Negative 2, 2. You've got nice fancy graph paper. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'll draw my own, but you've got some pretty graph paper. And then I'm going to do walk 2, climb 2. Negative 2, 2 there. Negative 1, 1. 0, 0. 1, 1. And 2, 2. So the shape of this absolute value function makes a nice V. And it turns out that all of our absolute value functions make that same shape. They're going to make a nice V, you know, a V like this or a V like that. Absolute value, always remember that makes that V shape because it's value, absolute value. So all of our absolute value shape functions are going to look something like this. And this is the parent. This is the simplest of them all. And those are the 5 points that I want you to graph. So if you've done that neatly right now, look, you've done 3 problems from that first homework. You've done your linear, you've done your quadratic, and now you've done your absolute value. But you are going to want to know these. So just like I said before, if you were actually in class, I'd have you graph them over and over and over again until you got really good. So you want to make sure that you're learning these points and these shapes of these functions. Okay, so there's our absolute value function. Let's talk next. See if you can figure out what makes this one, all these the same. See if you can figure out what kind of function this one is. So I'll give you a bunch of family members first. We got, how about 5? 5x cubed minus 2x plus 5. Or in function notation, 7x cubed minus 2x squared. Or we might even say it like this, where we've got x minus 4 cubed, and maybe that's being multiplied by a 1/2, and we're adding some number on the end, something like that. So what type of function do you think that is? What do you see in all those? What kind of function do you think that one is? See if y'all can come up with it. What do they all have in common there? Get my graph paper ready. Well, y'all think about it. So, did you notice they all have a 3? Their largest degree, or their largest exponent here is a 3. So, nice try, nice try. All their largest ones have a 3 on them. So we call this a cubic. A cubic. Yeah, there you go, September. You got it. Cubic. Cubic. Ah, yeah. That's it. Yay! Way to be, September. Way to go, guys. Y'all got this. Okay, so we've got a cubic function here, and the simplest of those cubic functions is just y equals x cubed. That's the simplest. This is the parent of all of those family members. And we're going to learn how to graph all those family members. So, or in function notation, it's just that f of x equals x cubed. And the shape of these guys, they always remind me here in Temple, you know, the cubic, 3rd Street. Have y'all ever driven down 3rd Street in Temple? I don't know how many people do this, but every morning on my way to TC, I drive down 3rd Street and I think to myself, I'm driving down a cubic function. Because our cubic functions look something like this, where we come and they're going to have a couple of little turns in them. And for me on 3rd Street in Temple, you know, I'm driving along and this is where I pay my water bill and, well, first there's the taqueria and then, you know, Tres Magueyes, and then there's the, where I pay my water bill, or maybe you've had to pay a ticket for parking or whatever, that building, and then a little bit further down is an oil change place where they're always outside, hey, there's no waiting, and then the new fire department that's there, and then Jack in a Box. So 3rd Street looks like it. So I can always remember 3rd Street, don't we all? Yeah, we can't leave the house. We can go through drive-through to get Trace. That works for me. Okay, so there we go. We got 3rd Street, or this cubic function is going to have that shape to it. Some of them will be a little more pronounced as we graph them. Some of them will look like this, or maybe they'll look like this. And we'll learn to graph all of them later. But today we're just going to look at that parent. And so we do that same exercise where we ask ourselves, is there anything that we can't put in for x? And we try a couple of ones that we think might be weird, like maybe let's try a 0. And if I put in a 0, well, 0 cubed is just 0. So 0 cubed is 0. So there's a point on this function at 0, 0. How about a negative number? Let's try it. If I put in a -1. Oh, well, -1 times -1 times -1. -1 times -1 is 1, times -1 gives me a -1. So I have a point here at -1, -1. And that was fine. So again, it turns out I can put in any number. I can even put in a fraction in there, you know. 1/2 cubed, we may not like to, but we can do it. Because 1/2 cubed is just 1/2 times 1/2 times 1/2. And remember, with fractions, the way we multiply fractions is straight across. So 1 times 1 is 1 times 1 is 1. 2 times 2 is 4 times 2 is 8. So there should be a point on this function at 1/2, 1/8. All right, so we can put in anything. So our domain, again, is that fancy all real numbers. X can be anything. We're talking about x. X can be any element of the real numbers, anywhere from -infinity to infinity. So that's the domain of this thing. So at -2, if I put in -2, well, -2 times -2 is 4, times -2 makes that a -8. On the positive end, I'm going to put in 1 and 2. 1 times 1 is 1, times 1 is 1. If I put in 2, I get 2 times 2 is 4, times 2 is 8. So those are 5 points on this graph. Negative 2, negative 8. Negative 2, I haven't put enough lines on here. 5, 6, 7, 8. Negative 2, negative 8. Negative 1, negative 1. 0, 0. 1, 1, and 2, 8. Those 5 points. 5, 6, 7, 8. And now, again, because it's all real numbers, that means there's stuff going on in between. So I'm going to connect all those dots. So it's going to look something like this. There's my parent of my cubic function. So remember September when we did square roots? And I did something like this where I get a negative 1 in there? Good question. So when I do the square root of negative 1 and I say, okay, what times itself gives me negative 1? You know, there's not a number where I can multiply by itself to get negative 1. So if I try, 1 times 1, that doesn't give me negative 1. If I do negative 1 times a negative 1, well, that gives me a positive 1, not a negative 1. And so, that's not, positive 1, so that's not that. Yeah, there's nothing that I can, in fact, if I do this, those two aren't the same, so it's not the square root of that. So we have just defined the square root of negative 1 as I, or this imaginary number. He's not real. So that's an example of one that's not real. So that's what I mean by that. So we'll see that here in a minute when we talk about our square root functions. I'm going to ask you that same question. Can I just put anything in there? Then your answer is going to be, I bet you can answer it when we get there. Okay. But until then, let's talk this cubic function. So our cubic function, cubic function. And here he is graphed. The only thing I need to do then is label my points. And now I've done 4 of my parent functions. Negative 2, negative 8. There, I've graphed 4 of them. 3 more to go. All right, so next, let's look at this guy. So far, so good? By the way, I keep talking about the domain, and I'm ignoring the range. But let me tell you about the range for a minute. So the domain talks about our x values. And the range is the y values. So if we look at this particular graph, and we think about our y values, is there anywhere that any number that our y is not going to be? So if we look at this picture, we can see that it's going to fill up the whole graph. Graphically, you can kind of visually see that the whole thing's going to be filled up on our y values also. Or for any number I put in for x, I can get out some every y value can come out of here. So it turns out that our range is also all real numbers. This thing's going to fill up the graph completely that direction, and it's going to fill it up and down. So our range in this one is also all real numbers. Again, we're going to have a whole lesson on range and domain, but this is really kind of scary talk and notation. So I like to be able to show you it ahead of time so that when we get there, maybe it's not quite as scary. And that just means that our y values can be anything also. Okay, let's do, how about this next one? 3 more. And so let's see if you can figure out what is all in common with this one. I'm going to write it in a fancy way, see if you can, see if you remember. So what do all those guys have in common? Oh yeah, there you go. I don't know who that, I need to know who the Rado-Nu is. Whoever that Rado-Nu is needs to comment in the Discord and let me know so I can give you a bonus point there. So we got September Austin and Rado-Nu all getting a bonus point. Because that is a cubed root. Notice how all of them have a cubed root on there. So here this is a cubed root function. Oh, Rachel, should have known. So there's our cubed root function. And remember, this one looks funny, right, with that 1/3 on there, but remember this part is the root. So this is just a fancy way of writing that same cubed root. So the simplest of our cubed root function is just y equals the cubed root of x. Or, in function notation, y equals, or f of x equals the cubed root of x. And our cubed root functions, well, let's graph it and we'll see what it looks like. But first, let's decide, is there a number that I can't put in for x? So first, let's do 0, because 0 is always nice and fun. So if I do put in 0 in there, the cubed root of 0 is just equal to 0. Okay, we can do that. We get an output there. We get out that output of 0. So when we put in an input of 0, we get an output of 0. That's all right. It's real. Now, what about that -1 in here? We just got through talking about the -1 underneath the square root. What about under the cubed root? Is it okay to have that -1 under the cubed root? So, you know, I'm asking myself, what times itself 3 times gives me -1? And you are exactly right. That's fine. Because -1 times -1 times -1 does equal -1. So it's okay to have a negative underneath the cubed root. I'm still going to get out a real number out of there. So the cubed root of -1 is equal to -1. So I can put in a negative number. I can put in a fraction. I can put in, you know, any number I want to, any real number I want to, and I'm going to get out a real number. So because of that, I usually use those same 5 ones, right? Usually we've been doing -2, -1, 0, 1, and 2. But when I put in -2 here, let's think about this for a minute. If I put in -2, there is a number that I can multiply by itself 3 times that will give me -2. But is it pretty? There is a number there, but is it a pretty number? And you know, what times itself 3 times it gives me -2? It turns out it's just not a pretty number. So instead, I want to think about what would be a pretty number that I could put in that would get out a pretty number. In other words, what can I take the cubed root of that I'm going to get out a nice integer, a nicer number in there? And if I had left up the cubic function, so go back to this cubic function, and we had these points, -8, -1, 0, 1, and 8. On the last one we just did, we had these numbers where we cubed them. So you can see that -8 is a nice perfect cube. So when I take the cubed root, I'm going to want to use these values because they are nice pretty cubes. Yeah, 16, remember that 16 for the square root. Because when I get to the square root, 16 is a nice perfect square. And we're definitely going to want to use that when we're thinking about square roots. But here, because I'm thinking about cubed roots, I want something that comes out as a nice number. And looking at my cubic, I can see that these guys are perfect cubes. So if I put in -8, I'm going to get out of my cubed root a -2. Oops. So don't put in -2. Instead, let's put in -8. Because then we get out a -2. So notice that from my cubic to my cubed root, these values kind of swap places. My x and my y's are going to swap places. If I put in just a +1, then the cubed root of +1 is also 1. And then I'm going to want to use that 8 to put in for x here so that I get out a nice pretty 2. So notice my cubed root and my cubic function are related here. Their x values and their y values just swap. We're going to learn next week about these things called inverses, and we're going to find out that these two are inverses of one another because their x values and their y values just kind of swap places there. So I can, with cubic functions, also put in any real number, but notice I didn't use those same 5. They ended up in the y value instead. So my domain, though, is still all real numbers. Okay, I'm going to graph those 5 points, 0, 0, 1, 1, and 8, 2. This direction, -1, -1, and -8, -2. So that the function looks something like this. Now to me, it's still 3rd Street. You know, I'm still driving along, hit the taqueria, hit that place where I'm paying the water bill. I'm still doing that on that curvy road. It's just sideways now instead of up and down. And to help me remember which shape goes which one, because sometimes I might get confused about it, this one is, the 3 is up on top, so it helps me remember that it goes up and down like that. Whereas on this one, the 3 is on the side, so it helps me remember that, you know, the cubic function is on its side there. I mean, the cubed root, yeah, it takes the cubic function and turns it on its side. So the cubed root function is sideways. So that's just how I remember the shape of them. Cubic is straight up and down, and then the cubed root is sideways. So there's the parent function of that cubed root function. So we label the points, and we're done with 5 of our parent functions. And so far, on every single one of them, the domain has been all real numbers. So our x values could be anything that we want. All right, 2 more functions. Last 2. So, see if you can figure out what all these guys have in common. Uh-oh, that black is dying on me. Try this blue. See if you can see the blue. Y equals or maybe do f of x equals I don't know, something like this. Or maybe we have a function that looks like this. So what do you see that all of those do? Cheyenne, I'm just going to teach until I've got the concept done. So we're going to graph 2 more functions, and then we're going to be done tonight. And on Thursday, I'll graph transformations, and it's just however long it takes me to graph transformations. If it takes me from 6 to 9, then I do it from 6 to 9. If it just takes me from 6 to 7, then I just do it from 6 to 7. So I'm just going to be on here and teach like I normally would have in the classroom. Yay! Square root, you're exactly right. They're all square roots. And so even this one, remember, it's just a fancy way to write. That exponent means this square root. Those two things are the same thing. So our parent of them is just y equals the square root of x. Or in this fancy function notation, f of x equals the square root of x. Now, when I get ready to do this one, and I start thinking about the domain, or what my x values can be, is there a number that if I put in it, if I input it, I'm not going to get out a real number? So think about what can I put in that then I get out. Perfect. Sounds good. And if something happens and the baby's crying, or something happens and y'all can't be here during this particular live stream time, what I'm going to do is I'm going to post the video then in D2L later, and so you can watch it at your own leisure, or leisure. As you're sitting around the house and the baby's finally asleep, then you can watch it then. So I will post these in D2L. So, I like 16 because 16 is a perfect square. But is there a number that I can't put in for x? Like, what value would not be good to use as my x value in this one? Can you think of one? So what about 0? I always like to start with 0 to see, does 0 work out? So can I take the square root of 0? Sure, square root of 0 is just 0. That's a good number. What about the square root of 3? Can I do the square root of 3? Remember when we talked about square roots? We said the square root of 3 is somewhere between the square root of 1, which is just equal to 1, and the square root of 4, which is equal to 2. So this square root of 3 is somewhere in between there. It's like 1.7-ish, somewhere in there. So I actually get out a real number in there, out of there. I can put in 3, it's just not a pretty outcome. Whereas putting in 1, I get out a pretty integer outcome. And if I put in 4, I get out a pretty integer outcome. Same thing with 7. If I put in 7, that's between 4 and 9. 9 is a nice, pretty perfect square, so I get out 3. So that 7 is somewhere in between 4 and 9, closer to 9 maybe than to 4, again like maybe 2.7-ish or 2.8-ish, somewhere in there. So these are real outputs, but Austin, you're really close. I can't put in a -1, because if I put in a -1, if I put in a negative value, remember, yeah, there you go, Rachel, a -2. Any negative number I can't put in. Because the minute I put in a negative number, this is just defined as an imaginary number. There's not a number I can multiply by itself to get -1. So we say any negative number is restricted. This domain is restricted. We can't put in anything less than 0, or we're going to get out these non-real numbers. So we have to this time start at 0. It's the smallest number I can put in there. So my domain, I'm going to write it for you in this fanciness. My domain is x has to be bigger than, or it can be equal to 0. But this time it's not all real numbers. There is a restriction. It's got to be at least 0, 0 and bigger. Or in that interval notation, we start at 0, and then it can go to infinity. But its beginning spot has got to be 0. That's the smallest number it can be. So I'm going to put in 0, and when I put in 0, I get out 0. But now, I do want to plot nice, pretty points. So you are right. Putting in 3 is not a number I want to use. Putting in 7 is not a number I want to use. They just don't give me nice integer numbers. There are numbers on there, but they're not nice integer numbers. So instead, I'm going to use 1 because it's a nice perfect square. I'm going to use 4 because when I put 4 in here, I'm going to get out 2. And then I'm going to use 9 because when I put in 9, I get out 3. And remember that 16 earlier? 16 could be your next one, 16, 4. But typically that goes off of our graph, so I don't usually use it. These 4 are the only 4 you have to graph for me for the parent function. So on your parent square root function, it's just going to have these 4 numbers, or these 4 points on it. Whereas all the other ones had 5 points. All right, let me graph those 4 points. And let me grab the red to make my axis. And we'll look and see what that square root function looks like. Gotta go all the way to 9 since I'm inputting 9. So there's a point on my graph at 0, 0. There's a point on my graph at 1, 1. There's a point at 4, 1, 2, 3, 4, 2. And another one at 9, 3. But we see that there's also a point at 3, 1.7-ish. You know, if I go to 3 and 1 in a little bit, there's going to be a point on there. And if I go to 7 and 2 in a little bit, there's going to be a point on there. So this graph is going to look something like this. I could do numbers in between there too, and each one of them would have a point on there. There's an infinite number in there. It's just they aren't pretty. The pretty ones are right here. The integer points are there. So 0,
oh, it was 22
0,
minutes
1,
ago.
1,
Or is that
4,
7:22?
2,
We're slow.
and 9, 3. So our domain is restricted. And we can see that our domain is restricted. Notice that there's nothing happening on this side of my graph. If you go looking at the other 5, it fills up the graph paper both left and right. Your x values cover the whole thing. But here, my domain is restricted. There's nothing going on this side. My x's start at 0 and go to infinity. Notice also that my y's are restricted. I don't get any range values or any y values. Think about your y values. They don't start until we're at 0 also. And it goes from 0 to infinity for my y values also. So even my range here is restricted.
Right.
So there's your square root function. So now you've graphed 6 of your parent functions, those most basic functions. And our square root function just looks like, the spout on my teapot. When I was little, it was like, I'm a little teapot, short and stout. Here's my handle, here's my spout. When I get steamed up, hear me shout. Stick me over and pour me out. Y'all remember that song? There's my dance. That's all I can do for dancing. You've now seen my singing and my dancing. And if you were kindergartners, you would tell me what a great singer and what a great dancer I am. All right. That's the only time I miss my kindergartners is when I'm like, aw, they would say how good I am. But adults are honest. They're like, stop.
What's dangerous?
Okay.
That's crazy.
One last function that we're going to do. The last function we're going to look at looks like this.
Something sensitive and she.
See if you can figure out this family member. Here's another family member. Or maybe we got something like this. Ooh, that's crazy. Nobody here. That's weird, because nobody's here. Are y'all in Discord, I wonder? Maybe somebody entered the Discord chat. But nobody's in my house, just me. No men, I promise. I have two boys, but they're nowhere around. They're off in their rooms. Okay, so they gasp. Oh, no telling. Maybe one of my kids walked by and I didn't realize. Notice that each one of these has an x in the denominator of that fraction. And you are exactly right. Cherish, way to go. Another bonus point there. Boing. Oh, I bet it's from Discord. If you're in Discord, I bet somebody's talking in there. Way to go, Cherish. You're right. This is a rational function. Because my x's are in the denominator down there. And in fact, remember that x to the negative 1 means 1 over x? Oh, way to go, September, you're right. So our domain is restricted because the bottom cannot be 0. You're exactly right. So when I get ready to graph this thing, at 0, we go, hey, I know that if I put 0 in for, first let me show you the parent. The parent is 1 over x. That's the simplest of those rational functions. Or f of x equals 1 over x. And you're exactly right. If I try to put 0 into the denominator, that is undefined. We can't do that. There's not a number I can multiply 0 by to get to 1, so that's undefined.
She was typing a second ago.
And so right here, there's going to be a problem at our graph.
Here she is, just typing.
Undefined. Undefined.
How long ago was it that I messaged her?
That's the problem. And in fact, let's go ahead and let me show you what that's going to look like. There's this issue or this problem. Because x can't be 0, on my graph,
157 offline and 31 online is 180.
At where x is 0, there's going to be something that we call an asymptote.
What?
We go, hey, x can't be here. There's not going to be part of the graph.
Subscribe, please, and tell people that we need it. If we have 1,000 subscribers, we can stream from our phone.
There's a problem there in my graph. X can't be there. And we're going to look and see what happens to it here in a minute. So x can't be 0, but what about our other numbers that we usually use? Like, for instance, negative 2.
What is that? No idea.
If I put in negative 2, well then that's just equal to negative 1/2. That's all right. So I can use that same negative 2, negative 1/2. That's okay. If I put in negative 1, well, 1 divided by negative 1 gives me a negative 1. So there is a point on the graph at negative 1, negative 1. Let me go ahead and graph those. So at negative 1/2, negative 2, there's a point on there. And at negative 1, negative 1. Is that what I said? No, it's negative 2. Oh, I'm sorry. Negative 2, spoiler, spoiler, spoiler. Negative 2, negative 1/2. That's what it looks like. But I want to see what's happening as it gets close to this line here. Like, as it's getting close to that asymptote, what exactly is happening to my graph? So let's pick a value in between 1 and 0, or negative 1 and 0, to see what is happening right there. So let's put in a negative 1/2 and just see what we get out. So if I put in a negative 1/2 for x, so that I have 1 divided by a negative 1/2, well, we know how to do division. Looks scary, but we got it. It's just 1 divided by a negative 1/2. So you're going to keep the first part. You're going to change your sign from division to multiplication, and you're going to flip that guy. Keep flip, change. So keep him, flip that sign, change him, or just multiply by the reciprocal, however you want to say it. So 1 times negative 2 is equal to negative 2.
Is Leah M
So
probably one of yours?
point in here. When x is negative 1/2, we're going to have a point at negative 2. I want you to graph that point also on your rational function. So at negative 1/2, negative 2, we're going to have a point. And let's just think about if I made this a smaller fraction, like if I made 1/8. You don't have to write this one down, but let me just show you what happens. If I turn that all into 1/8, well, it flips still, and so I get 8, and I get -8. Notice that 1/8 is closer, and yet it's further down. If I put in 1/100th, it's going to get closer and yet further down because it's going to be -100. So the closer we get to 0, the closer we get to this asymptote, the further down my y values go. They just get smaller and smaller and smaller. So this graph is as it approaches 0, as it gets closer, as my x values get closer to 0, my y values get smaller and smaller and smaller. So it gets really close to that line, but it never touches it because x can't be 0. Then, going this direction, you know, if I put in a -10, so if I put in a -10 way out here, then my bottom is a -10, and I end up with a -1/10. So I'm getting really little. So the further I get out here, I get littler and littler and littler. So, you know, picture a -100 or a -1000. If I put in 100, or if I put in 1,000, just I get teenier and teenier and teenier. So the further my x's come out, the smaller and smaller my y's get there. They're getting tinier and tinier. They're getting closer and closer to 0. So as my x's go out towards infinity, out smaller and smaller that way, towards -infinity, my y values get closer and closer to 0, but they never touch it. So we have another asymptote right here where y equals 0. In other words, my graph is getting really, really close to that 0, or y equals 0, but it never hits it. So my graph approaches this asymptote and approaches that asymptote, but it never actually makes it there. All right, now let's look at the positive side. So, you know, let's put in a positive 1/2. Well, the same thing would happen with a positive 1/2 as happened with the negative 1/2, except it would end up being positive. So when I put in a positive 1/2, out comes a positive 2. So there's a point on here at 1/2, 2. That's right. The domain is going to be, you're right, it's going to be where, here, I'll write it here in just a second. Let me graph these points and then I'll show you. So we're at 1/2, there's going to be a point at 2. If I put in 1, well, I'm going to get out 1. And if I put in 2 in for x, well, that's just going to be equal to 1/2. So my x values here are at 1, 1, or my points are at 1, 1, 2, 1/2, and 1/2, 2. And again, it's as I put in smaller and smaller numbers here towards 0, this graph is just going to get, the y values are going to get bigger and bigger because those fractions are going to turn. You know, if that's 1/8, it becomes 8. If it's 1/100th, it becomes 100. It just gets bigger and bigger. So these get closer and closer to, as my x's get closer and closer to 0, that gets bigger and bigger. As my x's get bigger and bigger, this gets closer to 0. So there's my rational function. And you're right, the domain is really, x can be any number. Because notice, it's filling up both sides of my thing. It just cannot be 0. It can be anything except for 0. And in interval notation, we do it this way. We say it can go from -infinity all the way out to positive infinity, but it stops at 0. So in other words, my x's can go from -infinity to 0, and you can kind of see that. Here's one piece of the graph that goes from -infinity up to 0 and stops. And then there's another piece that goes from 0 to infinity. So you're right, September, it's on both sides. It can be bigger and it can be smaller. Yeah, use a ruler, Austin. I agree. Just neat, and organized. So I can read your work when you turn it in, please, please. Okay, so that's the 7th function. Be sure and label your points so I know what your points are. And that's what your first homework assignment is just to graph those 7 functions. Now, if you were in the class, I would want you to be able to do all 7 functions in 5 minutes. You're going to need to know the shapes of all of these functions. So that's number 1. You know, put them on your refrigerator so that you need the shapes. That's true. It does not help with the curves. I agree. And then then also what the shapes are, and then you want to know those 5 or 6 or 4 points. So all of them have 5 points that go along with them, except the square root function only has 4. And then the rational function, you need to know all 6 of these plus the asymptotes. So graph those, make sure you know those shapes, and then on Thursday we're going to move them around. We're going to transform them. And there are some videos online. You could go ahead and get started if you wanted to, but this is how we're going to do class as long as we're out, which I think is going to be the rest of the semester. So hopefully this live streaming helps. You can still get the feel of the lecture, and you'll see if you go back and watch any of the other videos, I included a lot more in this than I'm including in those videos. So hopefully it'll help you to understand it a little bit better. So I guess we'll say goodnight tonight. I'm sorry that I can't see y'all. Hope y'all are enjoying being at home in your pajamas and being able to snack or whatever, go to the refrigerator in the middle of it. So y'all have a great evening, and I'll see you on Thursday. So math made simple at Simpson Math. Y'all have a great night. Hey, subscribe so you know when I'm going live. Subscribe. I know I miss y'all too. Miss you too. Stay well. Don't get sick. Stay home so we don't all get sick.